Hello, everyone. My name is Chandler, student at Berkeley, currently studying both MCB and data science.
Hi, I'm Rashab. I'm a third year studying IUR and EECS.
And so today we're going to be presenting on the precision medicine platform that we've been working on at the American Heart Association. Um, and just to kind of get us started, I think it's important to kind of share the mission statement to be a relentless force for a world of longer, healthier lives. Now, of course, given the broad spectrum as to what exactly the AHA does, even I'm not too sure how many lives the AHA is really reaching out to, but I think Rashab and I here can really explain the kind of data science portion as to what exactly the AHA does. And most of that is going to be through the Get With The Guideline program, as well as the precision medicine platform. And to kind of get us started on this, I'm showing you basically the workflow of how data is essentially being transported from the hospitals. The American Heart Association creates multiple registries, the most recent one being the COVID-19 heart registries. There are also heart failure, stroke, resuscitation. And we get this information from over, I believe, 16,000 hospitals, many records from each of the hospitals. Each hospital basically fills out a registry or a form with all the data and sends it over to us at the AHA. And what we basically do, or what the data scientists basically do, is kind of clean up that data and basically transfers that data over to a larger database that researchers can essentially access on the precision medicine platform, which Rashad can explain a little bit more in depth.
So the platform itself is AWS based. So it makes it really easy for us to partition out workspaces for the researchers and other data scientists. The workspaces include access to tools like Jupyter Notebooks, RStudio, et cetera. So it makes it really easy for a researcher to just be given a workspace and then analyze the data or play around with the data however they like. Next slide, please. So since the COVID-19 registry through the AHA is one of the largest in the United States, it's really important for us to have a robust data and documentation section, as well as usage and examples, so that the ramp up time for researchers and data scientists is as short as possible. We really want them getting to work as fast as possible because the information results that they get are super important. Next slide, please. So my work this semester has been mostly on the front end, along with data visualizations. So right now, this is the current registry dashboard that's up on the website. There's thousands of variables here, some of them including administrative variables, reason of hospitalization, demographics, among many others. So there's a few things that are important here, like the documentation hyperlinks, summary statistics of the data, as well as like distributions. So the idea of this dashboard is for researchers or data scientists to just get a quick summary of the data and be able to look up whatever they need out of certain variables. So currently it's just a basic HTML table because the ramp up of the COVID-19 registry was so fast, they didn't have too much time to work on the front end. So next slide, please. Yeah, so here's where my work comes in. So each of these variables gets its own card. And the idea is to create a much larger visualization, as well as bigger, like the summary statistics is larger, things like that. We also have a mutate section where the data scientists or researchers can basically take sections of the data that they really want to see, and it creates a respective distribution or visualization for that. Next slide. Oh, yeah, here's how it would look. You can restrict the numbers how you'd like. Next slide. Similarly, we have a filter sort of card where you can filter based off of qualitative variables like race, for example, here, and it creates a respective visualization for that. Next slide. Thank you.
And most of my work at the AHA was actually more working on the back end. So currently some issues or some of the challenges with the Get With The Guideline registries is that, well, first, hospital staff needs to fill out each registry for every single patient every single time. These registries can last for anywhere from 5 to 10 pages. with an extensive fields for medical history and just a lot of information, and it's extremely labor intensive process. In addition to that, because these registries are kind of extracted separately, it's difficult for researchers to do any cross analysis on the different registries. And so what my work basically entailed is essentially creating an American Heart Association moderated data lake, or a large database where we can kind of combine all the different registries into one large database. And the way we were doing that is my peers and I are essentially creating a Django framework in order to kind of store everything in the back end, and then hopefully combine with Rishad's efforts in the front end, gives researchers kind of like the better platform to really see the data and to really work with it on the precision medicine platform. And so just to kind of wrap up the main things we've been kind of talking about and the actions we've been doing, essentially what we're trying to do is simplify the method of data collection directly from electronic health records and being able to map it to that large database that I'm creating. In addition, we're trying to create a simple, streamlined process of distributing this data to researchers upon their proposal approval. And finally, on Rishad's end, we're trying to kind of create a more improved user-friendly registries that can show quick summarizations and just any data analysis at a glance. Yeah, that's the end of the slide. Thank you so much for listening to everything we've been doing for the past semester. And yeah.
So any questions? So if nobody has a question, I have a question. So I wanted to ask you guys, like, what are some of the issues that you faced with respect to like dealing with such a large data set? And also like, patients' data is also very, it's private in some sense. So like, how does privacy come into picture as well?
Yeah, I can take some time to answer that. Obviously, most of this patient information is somewhat NDA. Although most of the data does remove patient identifiers, still technically, we're not really allowed to release it unless the researchers really have like a proposal and like there's an agreement between the researchers and the AHA. But that is, in terms of like security, that is still one of the main issues. We do have this database, but we still have to kind of figure out how exactly we're going to be securing it. So that's kind of a topic for future discussions.
Yeah, in terms of dealing with the size of the data set, that's why the back end is so helpful. Allows us to do a lot of that pre-processing that we need for the data, especially since we collect all the data for the registries through Google Forms, and a lot of them are user inputted fields. So that leads to a lot of error, right? Some person can misspell a certain condition, they can type it differently, things like that. So a lot of that pre-processing is really helpful. It's really helpful to do that on the back end.
Any other questions?
This is Jen Hall from the AHA. I just want to say these two have done a terrific job in working for us. And I just had one question for both of them. How does this experience differ from what you're doing in the classroom?
Question. Also, I guess I can take a small moment to also thank Jen for everything she's kind of done for us. She's been kind of leading us through our experience. In terms of the difference, I would most likely say, I mean, classes at Berkeley, you do learn all the concepts, but there's not really that much of an application. I think this experience has kind of really helped me, at least, really put concept to application, being able to kind of learn what I know about data sets, actually create one by myself, and also know that the data set or like the work that I do actually has an impact in the medical field or just in the healthcare field overall. And I think that's very worthwhile for me.
Thank you.
Yeah, thank you so much, Jen. Been a great help this semester. I definitely learned a lot. The huge difference that I see, at least I'm taking Data 100 this semester, and a lot of the data is given to us like pre-processed, or we have to do very little processing on the data to be able to get sort of the features and analysis that we want from it. The difference in the real world is that a lot of that data isn't really processed for you. Like I said before, a lot of the data is user inputted, so you have to sort of clean all that, and then it's also on a much larger scale, so you have to figure out how to deal with all of that through like various methods, like using a backend.
Okay, thanks.
Any other questions? Okay, so thank you so much for sharing your presentation today. And now let's move to the next team. Are the presenters here?
Yeah.
Hi.
Okay.
Yeah, we're here. Okay, I'll just share my screen then.
Sure.
All right. Thanks for joining us today. So we're going to be presenting on our data science discovery topic, which we worked in collaboration with the Food and Agriculture Organization of the United Nations to develop a standard phenology crop signatures for training Earth observation classification models. And now that sounds complicated, but basically we are trying to develop a crop mapping solution using satellite imagery and computational tools to estimate agricultural statistics in the sub-Saharan country of Senegal. And how we are approaching this problem is by splitting our team into two groups, depending on to tackle both, to develop a classification method for both large data sets and small training data sets. Now, in case we have a small training data set, we have team A working on convolutional neural networks, and in case of small training data sets, team B works on an algorithm, a model called dynamic time warping. And our goal is to use these models and develop and display predicted crop growth patterns on a user-friendly front end. So now Fakhri will be talking about the kinds of data we're dealing with.
Yeah, so the data provided by the FAO was approximately 500 gigabytes worth of satellite imagery from the Sentinel-2 satellite of Senegal for every 3 days in 2018. And what we have is like two bottom of atmosphere composites for each tile, with each tile representing a singular like area of an agroecological zone, and the combination of tiles making up the whole of Senegal. And both composites were multispectral, so they contained NDVI, EVI, red, blue bands. The main one being the NDVI, the Normalized Difference Vegetation Index, which assesses whether the target area contains live green vegetation and how vegetized it is, so to speak, at that current time. So NDVI takes on values between 0 to 1, and very low values correspond to more barren areas. Moderate values represent shrubs or grasslands, and high values indicate temperate conditions. So the NDVI values here are good indicators of how far along a crop has grown in its life cycle. We also had the boundaries of different agroecological zones in Senegal. As you can see on the side, that is an example of a vegetation mapping for a singular tile. And from the crop sample data, we have polygon areas for each crop, from which we created shapefiles for collection so that we can distinguish crop NDVI change over different months.
Yeah, so at the start of our project, we kind of we were told to look into literature and past research and see what methods had the best success rate, and kind of decide on a method to use for crop classification. And my team kind of looked into a lot of research and literature about CNN, convolutional neural networks. And we wanted to approach that. So pretty much we focus on NDVI because as Fakri kind of noted earlier, it's like pretty important for crop classification, and also in the literature, they often stated that NDVI gave them the best accuracy, like training on that. So we used R to kind of extract crop labels as well as NDVI from like the rasters um, and the crop sample data. And then pretty much we ended up using transfer learning. So we used ResNet 18. That way we have a greater accuracy, and it's like less work also to perform deep learning. And yeah.
Yeah, so for Team B, what we did is extracted NDVI from each satellite image to form a time series and create a dynamic time warping function to predict future values. So dynamic time warping is used to compare the similarity between two time series with different lengths or speeds. And we use dynamic time warping to associate the time series of satellite imagery with the temporal sequences of our training data. And we have a couple of examples on the slide, but these are NDVI time series for crops such as airseed, rice, sorghum, and millet. But basically, we just applied dynamic time warping to recognize patterns over time of land use and cover classifications. So we could identify crop successions and rotations to distinguish like any seasonal variations in future years. And in the end, using the results from our dynamic time warping analysis, we can create like a rasterized time series, visualizing how land covering changes over time, which is this picture here with all the different colors.
Yeah, so one of our final deliverables for this project is going to be a dashboard. It's still in the process just because, yeah, it's still in the process, but pretty much our goal is to kind of make an interactive tool to allow users and even policymakers and whoever needs that information to perform crop classification and kind of be able to visualize crops and growth patterns and all of that.
Okay, so we talked about what we did, but just a quick note on why this project matters. So the underlying issue is that a lot of these sub-Saharan countries depend on agriculture for the bulk of their economy, but there's no really definite, efficient way to find out which crops are growing each year, which crops are facing a surplus or a shortage. So through our project, we try to contribute to the modernization of their agricultural statistics programs, because currently most countries rely on surveying or census making, and that's expensive and time consuming. And it's also impossible in politically unstable places like Afghanistan. So our method of remote sensing using satellite imagery will be revolutionary, both fast and cheaper than existing methods. Oh, and not to mention more accurate if we develop if we optimize the algorithm. So if we can contribute to the modernization of their agricultural statistics offices, it'll also help these countries improve their food security policy making, because they'll be able to make quick, accurate forecasts. So yeah, that's about it from our presentation.
Thank you.
Thanks for listening.
Any questions for the team?
Hi, I have a question. This is a little more lighthearted. I just was wondering, what was your favorite part about working on this project? Anyone can answer.
Can I go? Yeah. So because this was a project that involved so many different kinds of data and such heavy data, that it often took time to get a lot of our tools working, like Microsoft Azure or some of our algorithms to work. So my favorite part was when we got some of the most complicated algorithms or tools to work on our data. It was very fulfilling.
Yeah, for me, I guess I was most excited about the application of it. I do have an interest in like the agricultural field and environmental science. So I thought this was a really cool project to take on.
Yeah, similar to what Atharva voiced earlier, like just being able to use all these cool new tools that I didn't have previous experience with. So like we used like Azure ML, we had like a VM running, which is really cool. And like using geospatial libraries, that was a new thing for me. So just learning throughout this whole process was, yeah, it's great.
Any other questions? Okay, so thank you everyone for joining us today in this breakout room. And we only had 2 presentations here, so you could just jump in.
We have a third one. We were actually invited to. I don't know why we're not on the list, but we're here.
Awesome.
So
Okay. Sorry about that.
yeah, it's all good. So I'm gonna go ahead and share my screen for that one. All right. Cool. Okay, so we're Project AEI, and the basic goal of our project is to use AI for the development of a real-time system that can rein in police misconduct by the recognition of emotions. And so you do this by the prediction of like physical behaviors based on the kind of emotions that you're picking up. And so I'll pass it on to the next person in my team who's talking about data collection and organization. So I believe that would be Kalen, right?
Kalen, you're muted.
Kalen, I think you're muted.
Thank you. My bad. Okay, so we actually started working on this project last semester, and last semester we had to do all of our own data collection and we scraped from YouTube, but this semester we decided to take a more standardized approach. And so we pulled from a lot of previously created data sets that contained a lot of audio data and it had been analyzed for for 7 different emotions, 7 standardized emotions that are like universal within emotion. They're kind of they're the most basic of emotions. So that included happiness, sadness, surprise, disgust, fear, neutral, and yeah. Anyways, so a few of these data sets were TESS, SAVI, and RAVDES.
Cool. Another interesting fact about these emotions is that they're universal across the face, voice, and brain. So, it will help us in the future if we decide to build something else that takes in other kinds of data besides audio files. And so for the model, I'll pass that on to Varun. Varun and Jasper, whoever wants to speak about the kind of model that we built.
So for the model, we built a neural network with 3 parallel layers. So we first we have a CNN layer as well as a transformer encoder layer where we pass in the spectrogram to, and we have additional features that we pass into a 1D layer. So it's similar to the image to the right, but instead of a second 2D CNN, we have a 1D CNN. And so the reason that we use a transformer encoder layer is because we're working with like a sort of like time data audio. It's kind of like ordered, so there's like certain things that might require like more attention, and this is like for data that is like this is typically the like the recent like industry standard for how or for like modeling. And this worked pretty well compared to like the other things we tried, like just using no features and just like the spectrogram, and it achieved about 75% accuracy on the validation and test data. So here, this is a bit more on our data preparation. So to start, we augmented our data by adding Gaussian noise as well as some pitch shifting And this allowed us to bring our data set from around 10K samples to 40K. So quite a bit more. And then next, we sort of prepared our inputs for the model. For the convolutional layers and the transformer, we had to get the MEL spectrogram. So that's the image on the top right. And then we also computed additional features like the zero crossing rate. So this is like sort of like a measure of like how often the audio has like a sign change. And then we also computed the root mean square energy. So just like the energy of the audio signal. And those are pretty helpful features for emotional recognition. Yeah, so this is sort of like a graph of like the training performance on the training set and the validation set. You can see that like after around like epoch 20, the validation loss is like not really improving, while training loss is still decreasing. So there is like quite a bit of overfitting, which is pretty common in neural networks, but we tried a few things to like regularization as well as like augmentation to improve this, but it still ended up overfitting a bit. But yeah.
Yeah, so the end goal of our project is to basically integrate this neural network into an app that users can use. And so this semester we worked mainly on developing the front end of the app, and we're still working hard on the back end. But just to guide you guys through our app currently, we have the home screen on the left side of the slide. And then the app will allow users to basically record their voice, and it listens to the user talking about their feelings. And then once the user stops recording, then the idea is that in the back end, the neural network would analyze the user's voice and its various features, and then provide like an emotional prediction. And then on this screen, then the user can then select whether or not the emotional prediction was correct or not. And if the prediction was incorrect, then the user has an opportunity to then correct the model by selecting which emotion they're really feeling. And so you can see that on the screen on the left of the slide. And then on the right, this is the case where the prediction was correct. And then in this scenario, the app would then provide the user the opportunity to either get like a music recommendation, so something that would enhance their mood, or like, I guess, describe the user's mood in its entirety. Or it allows users to receive a behavior recommendation. So this recommendation would then basically show the user whether or not their current mood is violent or non-violent. And the ultimate end goal of our app is then to be used in a police setting, such that in the case where a police officer may be getting a bit too aggressive, then this app would remind them to, be more conscious of their feelings and be mindful of the people they're working with. So yeah.
Okay, so yeah, as you probably saw in our presentation, there's 3 prongs of our project, which is the actual pre-processing of the data by spectral analysis, spectral features, building the transformer models, and then designing the overall front end of the app that we just displayed, at least from like a I guess different screens perspective. But yeah, the overall purpose of the app, besides I guess allowing officers to be more mindful of their mental states when in the field, is probably to allow maybe police departments to be able to be in touch with officers on the ground, so that we can kind of rein in police misconduct in real time, by providing police departments with kind of like a real-time view of what's happening in the environment is the end-all goal. So hopefully we can save some lives in the future, essentially. And so with that being said, I believe that concludes our presentation. So if anyone has any questions, feel free to ask.
Any questions for the team?
Yes, I have a question. So what's the rationale of adding Gaussian noise to your input?
I believe that's a question for Jasper or Varun, right? So go ahead, guys.
So I think Jasper mentioned this while presenting, like he touched on this, but we were mainly trying to reduce the overfitting that we were seeing in the model. So training accuracy, training loss being very low, while validation accuracy not being as low, and noise is like in some cases has the potential to have a regularizing effect. So that was our kind of thinking behind that.
Oh, I see. So basically, you deliberately make it the data dirtier to overcome this overfitting.
Yeah. So we tried that. We tried dropout layers, as well as a few other things that Jasper mentioned during the presentation to reduce overfitting.
Interesting. So have you, I think maybe you mentioned, but I might have missed. Have you ever considered that this overfitting might be caused by the inadequacy of the complexity of your neural network? Basically, the number of parameters or the space of the parameter may not be sufficient for the complexity of the model.
Yeah. I tried like decreasing the number of parameters and like layers for the model, but it didn't really have like that big of an effect, and sometimes it was like worse.
I see. Interesting. Thanks. Oh, we're going to be good.
Okay, so thank you everyone, and see you in the main room now.